This actually worked out pretty well for us with last week doing 7 and 8 and then saving chapter 9 for this week because that's the only thing that we're going to do tonight is going to be chapter 9, magnetism, and this is a huge chapter. I don't think there's any other property that has had such a profound impact on society as magnetism, as you're soon going to see. I mean, if it weren't for the property of magnetism, electronics and electricity would not be what it is today. It's really that simple. So with that introduction, let's forge ahead with chapter 9, magnetism. After completing this chapter, you're going to be able to identify 3 types of magnets, describe the basic shapes of magnets, describe the difference between permanent magnets and temporary magnets, describe how the Earth functions as a magnet, state the laws of magnetism, explain magnetism based on the theory of atoms and electron spin, explain magnetism based on the domain theory, identify flux lines and their significance, define permeability, describe the magnetic effects of current flowing through a conductor, describe the principle of an electromagnet, describe how to determine the polarity of an electromagnet using the left-hand rule, define magnetic induction, define retentivity and residual magnetism, define a magnetic shield, describe how magnetism is used to generate electricity, state the basic laws of magnetism, describe how the left-hand rule for generators can be used to determine the polarity of induced voltage, describe how AC and DC generators convert mechanical energy into electrical energy, describe how a relay operates as an electromechanical switch, discuss the similarities between a doorbell and a relay, discuss the similarities between a solenoid and a relay, describe how a magnetic phonograph cartridge works, describe how a loudspeaker works, describe how information can be stored and retrieved using magnetic recording, and describe how a DC motor operates. I don't think we've had any chapter up to this point that has had so many objectives, and this just shows us the far-reaching hand of the property of magnetism. It's everywhere. All the magic that's done in today's society is brought to us really by magnetism. I'm not bragging about it. It's really what takes place. Magnets, natural, there's really several different types, 3 types. Natural magnet is derived from magnetite. And it just so happens that I've got a couple pieces of magnetite in my pocket. These are natural magnets, okay? It's like found in the Earth's crust. Here it is. So we'll pass this around and we'll let you play with polished magnetite, okay? So that's kind of cool stuff. So that's found in the Earth's crust, and it's just a natural magnet. Artificial magnet could be created by rubbing a piece of soft iron with a piece of magnetite. So if you've got a piece of soft iron and, I see underneath what the heck are you doing under there? I'm creating an artificial magnet by rubbing a piece of soft iron with a piece of magnetite. And what it's going to do is it's going to pull that magnetic property off of the magnetite and transfer it to your piece of soft metal. Actually, that's a trick with a lot of mechanics, right? If you magnetize the tip of a screwdriver, it comes in handy for picking up things that you drop into odd places. Finally, the 3rd type of a magnet is an electromagnet. This is created by current flowing through a coil of wire. Basically, when we pass current through a coil of wire, we're going to develop a magnetic field. And in concentrating that, that's how we have an electromagnet. So electromagnets range in size from very, very small to, if you've ever seen like at a junkyard, a scrap yard, on a crane, they've got an electromagnet. You turn it on, it picks up a car or whatever. Actually, my favorite application, I'm a big James Bond fan. Remember that Jaws dude? It was like biting things like train cars and stuff, and they turned on the big electromagnet and boom, pow, he gets pulled right up to the ceiling on that. So that was a giant electromagnet. I'd hate to have your credit cards anywhere near that, as your credit cards have magnetic strips on it, and a strong electromagnet will probably desensitize those cards. Here's some examples of some magnets. Come in variety. It's my personal collection. Just kidding. This is torrid core, meaning it's a donut shaped. It's circular. This is a standard bar magnet. This would be like a horseshoe magnet because it kind of looks like a horseshoe. The thing to remember is that all these magnets are going to have a north pole and a south pole. Even that magnetite that we're passing around there, if you try holding it unusual, it won't even attach each other. Basically, the reason that those four pieces of magnetite are attracted to each other is because the north pole is attracted to the south pole of the other magnet, which is attracted to the north pole, the south pole of the other magnet. North and north ain't gonna work. Permanent magnets retain their magnetic properties. That's why they're called permanent magnets. Temporary magnets are only going to retain a small portion of their magnetic properties. That's why they're called temporary. Okay, and over time that magnetic field may deteriorate or be altered. So permanent magnet will retain the magnetic properties. Now this is kind of cool, and I'm sure it's no surprise to any of you. The Earth is a giant freaking magnet. Okay, and it has to do with the core of the Earth and then the crust, right? But we basically have a giant north pole and we have a giant south pole. The problem about the north pole and the south pole, I got to give you a geography lesson here. If I wanted to go find Santa Claus, where would I look and how would I get there? How could I navigate my way to this place? With a compass. And where am I trying to get to? Okay, so you want me to use a compass to try to get to the North Pole to try to find Santa Claus? To get to the magnetic North Pole. If I get to the magnetic North Pole, am I going to find Santa Claus? No. Nowhere to be found. In order for me to find Santa Claus, what am I going to have to do? I'm going to have to go to the True North Pole, or the North Geographic Pole. The North Geographic Pole, which is literally the top of the Earth. Anybody want to take a wild guess what the best way of getting up there might be? What's that? Well, I'm talking about means of transportation. What's that? Submarine. Submarine, yeah. You could be in a short sleeve shirt and go up there, surface at the North Pole, because it's underneath the Arctic Ocean. So you could surface at the North Pole. So I just happened to flaunt that. I actually have never been to the North Pole. My submarine has been to the North Pole. At home, I've got water from the North Pole in a vial from my submarine that went to the North Pole. My submarine actually delivered, believe it or not, Al Gore to the North Pole. It was after I was off the sub, but they did a mission and went to the North Geographic Pole. And typically on the ice, they'd put a lot of research camps to conduct research, magnetic research, and that's the place to do it. So the North Magnetic Pole is, this illustration, it's an artist's depiction, it's not very accurate. The North Geographic Pole is going to be somewhere up here, up north of Labrador. And it moves about 2 kilometers per year. And it's actually moving in a northwesterly direction. And the variance, the magnetic variance. Does anybody know the magnetic variance? The difference here between the North Pole, geographic pole, and where the North Magnetic Pole is? I know because I'm a pilot. And it's kind of important. Okay, because if I start flying northbound or whatever, which am I going geographic north or am I going magnetic north? And the difference here in the Seattle area is between 19 and 20 degrees difference. It's pretty significant. So this hallway right out here in this wing is aligned pretty much with the North Geographic Pole. If you could walk straight, which none of us could do, we've got a dominant leg, and you walked out this hall and just kept walking north, eventually you're going to get to the North Pole, find Santa Claus. It's all going to be good. If you had a compass and you stepped outside the door here and you looked, that north magnetic pole is going to be literally over in this direction here. So it's very important because, again, in the aircraft, you've got a compass. You set your gyro compass for that magnetic heading. And I bet you folks never realized magnetic properties had such a profound impact on all these different things. If any of you are familiar with airports, airport runways are designated based on their magnetic heading. So SeaTac Airport's got 3 runways, but they're all parallel with each other, so they all have the same numbers, okay? If you're headed southbound, like typically when we have crappy weather here in Seattle, if you look up and you see an airplane going into SeaTac, what he's going to do is he's going to fly out over Lake Magnolia, right, then turn inbound, and then what he's going to do is land on runway 16. Because if you rounded that, it's on a compass heading of 160. So how do you make sure since there's 3 runways down there, because we all remember, those of us that have lived in the area a while, that 3rd runway when they put it in, it was very controversial. It's 16 left, 16 center, and 16 right. That's how they designate which runway you're cleared to land on. Add 180 degrees to that, and you end up with what? Runway... No, 16 plus 180 degrees, runway 34. So if you're landing northbound at SeaTac Airport, you're cleared to land on runway 34 center, 34 left, or 34 right. Okay. Ironically, and the reason that they select runways is they do wind studies to determine where the prevailing winds are. You want to take off into the wind and you want to land into the wind. So primarily here in central Puget Sound, that's pretty much how all the runways are. Auburn Airport, 1634. Renton Airport, 1634. SeaTac, 1634. Boeing Field is a little bit different. It's runway 31 northbound, so there's going to be a slight variance in runway 13 in the opposite direction. It's just how the winds are kind of funneled there by the location of Boeing Field. But Renton Airport used to be runway 33, but because of that magnetic precession, what they've had to do is they've had to renumber. And you think, oh, it's no big deal. You send a guy out there with a can of paint and you paint a new number on the runway. It's not that easy. All of the procedures, all of the approach procedures, all of the publications, all of the databases all have to be updated. It's really a big thing. So eventually, all runways are going to have to change their number as that north magnetic pole continues to fluctuate. Why am I telling you this in an electronics class? A lot of you are going to go to work in industries that are associated with electronic navigation. And you got to know this. I mean, you don't have to memorize it. I'm not going to quiz you on this magnetic precession and the 19-20 degrees variance here in Seattle. But a lot of you are going to go to work in electronic navigation systems, and you need to understand the difference between the two. Make sense? The laws of magnetism, I think most of you probably remember this from elementary school. Unlike magnetic poles attract each other, right? Unlike attract. So a north is going to be attracted to a south, the south is going to be attracted to a north. Like magnetic poles repel each other. North and a north, they're going to push each other away. South and a south, push each other away. This is actually kind of interesting too, because it has some applications now, like magnetic levitation. Some of these rail systems that they're actually, the whole train levitates magnetically. That's how they're doing it. That's how you get a whole train to levitate, because North Pole and the North Pole, they'll basically push each other away. And then once you've got something floating like that, it doesn't take a whole lot of energy to move a train. I mean, think about that. I don't know if you've ever even thought about why do we use trains. I mean, trains, that wheel on a rail, very little friction. So it takes very little energy to move a bunch of stuff, right? If you could kick it up even a notch further, I mean, we still have to overcome the friction of the bearings and the axle and the wheels on the track. Now, if you could levitate the entire train magnetically, then just give it a little push, and that thing's going to be able to move with hardly any energy. So these are a lot of the advancements that we probably want to stay tuned for because in the name of efficiency, we're trying to play with a lot of this stuff. Color code for magnets. color code for magnets. Red is the color code that we use for North Pole. Blue is the color code that we use for the South Pole. So if we were going in search of Santa Claus and we got to the North Geographic Pole, how would we know we got there? What would we see? Bzz. There'd probably be reindeer, but what color pole would there be? Red and white, very good. Red and white pole, we know that. Candy cane, right? If you're at the South Pole, what color would the pole be? Blue and white. Striped pole, right? I mean, if you got to follow that same tradition. If you're outside a place that has a pole that's red, white, and blue, where are you? Bingo. Excellent. Very good. I got students that just, same students that don't know what a barber shop is. I like the barber shop. That's how I roll. That's my thing. So yeah, that's the color code for magnets. Magnetism, the property of magnetism, can be traced to the atom. As electrons orbit the nucleus, they also spin on their axis. This electrostatic charge produces a magnetic field. So even these electrons are going to have magnetic properties. The direction of the magnetic field is the same as the electron's direction of spin. So even at a subatomic level, we're going to have properties of magnetism. Ferromagnetic materials, ferro meaning materials that contain ferrite. This is the stuff that will rust. Okay, if the metal will rust, it contains a high amount of ferrite. So any ferromagnetic materials are materials that respond to magnetic fields. Any of you have magnets at home stuck to your refrigerator? Okay, your refrigerator is made out of a ferromagnetic material. If it were not painted, it would rust. Plain and simple. If not, the magnets wouldn't stick to it. It's actually the old trick too, if you're going and buying a used car or whatever and you're looking for Bondo, right? Put a magnet over it, and obviously if it sticks, you know that's all original with no Bondo. You know, you all of a sudden get to an area and that magnet doesn't want to stick. Don't try this with a Corvette, of course. Corvette is fiberglass. And actually with all the cars now, with all the plastic on them, magnets aren't going to stick well to plastic. Atoms combine into domains or groups. When unmagnetized, the domains are random. This is what we're looking at here in this illustration. This is random domains. Okay? This is an unmagnetized piece of ferromagnetic material. As soon as we magnetize it, watch, this is kind of cool. Boom! When magnetized, the domains align in a common direction and the material becomes a magnet. So if you've got my magnetite that we're passing around and you rub a screwdriver up against that, this is ultimately what's going to happen. You're going to align those domains and it's going to become magnetic.
What was the difference between a ferrous and a non-ferrous metal again?
Ferro contains ferrite, and that's the iron content that makes stuff rust, basically. Now a magnetic field, this is kind of where you got to hit the I believe button, right? It's invisible lines of force that surround a magnet. These invisible lines are called flux lines. We've got to be careful because those of you in ELEC 115 are learning about flux, right? It's a different kind of flux. There's two types of flux in electronics. There's magnetic flux that we're talking about tonight, and there's also flux that we use as a cleaning agent for soldering, okay? You're not going to use a magnetic field for cleaning and soldering. To the best of my knowledge, and a magnetic field has never been used as a cleaning agent. Flux, however, is used as a cleaning agent, different type of flux. Okay, so this word has two meanings in electronics. And don't forget, one of the reasons that you're here is to learn the language of electronics. I wish I had had me as an instructor, Okay, because I was kind of like flux, and I was like, why are we going to use magnetic lines of force to, clean something to make it more solderable? Just, nobody ever explained that to me, and I wasn't the smartest student. These flux lines have polarity, and that polarity is north to south. North to south, and it always forms a complete loop. They do not cross each other, and they tend to form the smallest possible loop. Some of you may have done this like in 3rd grade. You got a magnet, bar magnet, you got a piece of paper, and on top of that piece of paper you sprinkle iron filings. The iron filings will actually form a pattern, and that pattern that you see is the invisible lines of force. It is the flux lines. That's exactly what you're doing by spreading those iron filings on that, is seeing the lines of flux as a visual aid, if you will. Permeability, there's a new word for you. Permeability is the ability of a material to accept magnetic lines of force. An example of something that has a high level of permeability would be your refrigerator at home, if you got magnets stuck to it. My last refrigerator that I bought, and how many of you here like buy a refrigerator because like you got nothing better to do? And like how many of you like buy a refrigerator because your food is all spoiled and your old one died? That's normally how you go about it. So, my last refrigerator, I was like in a panic and I found one, and and they never fit right. They've actually made them bigger. So if you want one to fit into the small hole, you got to get a custom refrigerator. So a smaller custom refrigerator costs more than the big one that doesn't fit right. So I just got the big one. It doesn't fit right. It's bigger or whatever. But I get home and I paid a lot of money for this thing. And then I get my magnets. And I got, the magnets to put Junior's work up on and everything else, and my favorite pizza place. Magnets won't even stick to this thing because it's like this designer facade. So you could, what the heck is this? So you got to put the magnets on the side. You got to put them on the side because the front is so that you could make it, I don't know. I just want something to keep my stuff cold. That's all I want. So permeability is a material that readily accepts these lines of force. If a magnet will stick to it, it has a high level of permeability. Now there's a direct correlation between electricity and magnetism, probably why we're talking about it tonight, right, in an electronics program. A magnetic field is generated when current flows through a wire, period. Period. Let me say that again. A magnetic field is generated when current flows through a wire, period. So, when you plug something into an extension cord, is it generating a magnetic field? You betcha. When you connect a speaker up to an amplifier and you've got current flowing through that wire to the speaker, are you generating a magnetic field? Yeah. Okay. Anytime current flows through a conductor, you generate a magnetic field. So, if you could see magnetic fields and you had an energized piece of equipment, you would see all of these lines of flux that are being formed by simply turning a piece of electronics on. By simply turning a piece of electronics on or an electrical circuit on, you're generating lines of flux. Sometimes it's something that we need to be aware of, other times it's something we need to discount. An example would be in your home. Okay? Typically how your house is wired up, the magnetic fields that are generated by your home are not sufficient enough to cause you any worries. They're not going to demagnetize your credit cards. They're not going to, screw up your brain. But still, they are generating magnetic fields. There's no way around it.
Wasn't there talk a while ago about staring at a computer screen for too long, the magnetic fields could affect you after a while?
Yeah, and again, with some computer screens, there's some higher frequencies that are used, and it's the same thing. Is it harmful or harmless? I don't know. There's also some laws on the books about building schools underneath power lines. You know, so if there was nothing there, why are there laws on the book about that? You know, I've never had an interest of, well, my only interest of living underneath a power line would be able to perhaps tap into that magnetic field and lower my power bill, which of course would be illegal and not above board, and I would never do that. But I never really had a whole lot of interest of like living underneath power lines, you know, because it's just an unknown. You just don't know, because those high voltage wires, they move a lot of current through it. I mean, you create huge magnetic fields. I don't know if you realize this, but if you get a fluorescent tube and you go underneath a lot of these high voltage wires, you could excite the gases inside the fluorescent tube and light it up. Look, Mom, it's lighting up with no strings attached. So if it could ionize gas inside a fluorescent tube, you know, what's it doing to your, you know, I don't know about you. You know, but I've had a pretty good life. I got a lot of good memories. I do not want to scramble those memories. So I'm going to keep my brain away from magnetic fields and anything else that will alter some of these fond memories that I have from my youth.
My journeyman told me that exact same thing. My mom was going to buy a house by power lines. And he said, well, go out there with a fluorescent tube and hang it up. And if it lights up, she don't want the house.
Yeah, yeah. So this is exactly what it would look like here. We have current flowing through a conductor, and we're going to generate this magnetic field around the outside.
I don't know if this is better or not, but you know, a magnetic field doesn't mean stuff's going to stick to it, right?
If the magnetic field is strong enough, stuff would stick to it. Normally, the magnetic field is not that strong, so stuff won't necessarily stick to it. Like iron filings are not necessarily going to be attracted, you know, to a low energy circuit that's energized. But that being said, there's still a magnetic field there. It's just not strong enough to, you know, attract an iron filing, you know, to stick to the circuit. Thank goodness. You know, or whenever we turned anything on, it would be, you know. Now, yeah, it would have to be a significant enough field to attract, you know, current to do that. The current going through it would have to be sufficient enough to create a big enough magnetic field to attract an iron filing. Electromagnets, composed of many turns of wire close together. Because as I just said, one piece of wire may not be strong enough. What happens if you get that and then you wrap it around again? Now you just doubled it. You do it a third time, you tripled it. Fourth time, quadrupled it. The math is simple. The math is that simple. So every time with a winding, you add a winding, you're increasing it, that magnetic field that you're generating by it. So the principle of an electromagnet, when wire is twisted into a loop, the flux lines are brought together. The flux lines are then concentrated at the center of the loop, and we establish a north and south pole. Anytime you create a magnetic field, you're creating both a north pole and a south pole. The strength of the magnetic field can be increased three ways. The more turns of wire, the more flux lines are going to be added together and concentrated. The greater the current, the greater the number of flux lines that are going to be generated. Okay, this only carries you so far though, because what happens, you're passing current through what? A piece of wire. What property does wire have associated with it? Resistance. So you just can't keep increasing the current, because if you keep increasing the current, eventually what's going to happen? It's going to become a fuse. I mean, even if the wire is this thick, you have enough current go through wire that's this thick, eventually you're going to part that wire, okay? And it's going to begin to get hot. And so it could cause an electrical fire. So you just can't keep saying, and let me take another step back. You know what kind of wire we're going to use to make these coils? We're going to use what's called magnetic wire. And magnetic wire is not wire that's inherently magnetic. Magnetic wire is wire that's used to make windings, and what it is thin copper wire, but it has a lacquer coating on the outside. There's an example right there, outstanding. That's magnetic wire. Okay? and it looks like copper wire, and it is copper wire, but on the outside is a thin lacquer coating. That lacquer coating acts as an insulator, an electrical insulator, to prevent the wire from shorting. Because if I wound wire over itself, why would current want to go all the way, keep going through the wire? It would just short right out. Okay, so we have to keep it insulated by using that lacquer on it. So let's get back to this bullet statement here. The greater the current, the greater the number of flux lines generated. I'm going to get to a point that I cramp so much current through that coil, it's going to begin to get hot. If any of you have ever done paint removal, you know that paint removal, when you're using a heat gun, works really, really good for removing paint. It works good on removing lacquer too. So once you have too much current go through that coil, you're going to compromise that lacquer coating, and that's the end of your coil. By the way, if any of you have ever smelt a coil, that's the end of the coil. By the time you smell it, it's over with. You've already compromised the integrity of it. It'll never work right again. Transformers, motors, coils, any of that stuff. Any of that stuff. If you smell it, if it gets that hot, forget it. Another way that we could increase the magnetic field is we could insert a ferromagnetic core into the center of the coil, usually iron. Iron has a high level of permeability. By putting it into the center of the coil and then wrapping the coil around it, it's going to enhance the magnetic characteristics. So by putting in a ferromagnetic core, it's going to enhance the characteristics. Now, magnetic induction is the effect a magnet has on an object without physical contact. The effect a magnet has on an object without physical contact. This is the cool thing, and I think some of you were playing around even with these magnets here, right? And how they're not even touching, but yet it's having an effect on the other magnet. That's magnetic induction. Residual magnetism is the magnetic field that remains when an object is separated from a magnet. We used to have literally a big problem with residual magnetism. This is something that I don't know if any of you want to make a wild guess at this here. I'm thinking of a very, very large object that developed magnetic properties, and those magnetic properties needed to be removed or it could compromise the position of this large steel cylindrical object. Submarine. Submarine. Big, big, big problem in submarining. Because the submarine, being made out of a ferromagnetic material, would pick up the Earth's magnetic field and gradually it would become magnetized. And the problem was there was equipment that would detect the magnetic anomaly. So there's no way of seeing a submarine, and some of our submarines are so quiet you would never even hear the submarine. But if you're flying in an anti-submarine warfare aircraft and you pick up a magnetic anomaly, a large submerged contact that's creating a magnetic variation, chances are you found a submarine. So this is exactly what, if any of you ever go up around Whidbey Island and you see those the big 4-engine turboprop aircraft, P3s. No, not those. Those are AWACS. Those are like airborne command posts. The P3 Orion is a submarine hunter, and off the back of it, you'll see like this little thing that looks like a stinger, and that's what that is called MAD gear, magnetic anomaly detection. So when you're flying around, typically what they just wouldn't be looking for a magnetic anomaly. What they would typically do is have a circular scan radar, so when they stick up a periscope, all of a sudden they get a blip, blip. If it's a good radar operator, that's all it takes, are two blips, and then he'll shut the radar down. So what they'll do is they'll continue to fly, and then he'll go to a sector scan. Okay, so from a circular scan, blip, blip, then he'll shut it off. then he knows where he's looking for because he saw it on the radar screen. He'll go to a sector scan, right? A sector scan is back and forth like this. So then it's going to be then he'll shut the radar off. And then he'll drive his cursor over to where he had that contact and hit enter. Autopilot will bring the airplane to that point in the ocean. And then the operator is looking at the MAD gear. And then all of a sudden they start to get a magnetic anomaly. At that point they pop a flare out over the target. If you're at war, at that point the aircraft is going to go into a bank, start to open the bomb bay doors, fly right over that point, put a torpedo in the water. It's a smart torpedo. It's going to find the target and blow it up. That's how you die in a submarine in a combat situation. Okay? The only thing that we would know, my job was to detect that, so I was good at picking up the blip blip. But again, the good guys, the good operators, two sweeps and they'd pick you up. The British came out with a radar that basically 400 miles away could spot a beer can floating in the water. So it's kind of like when I saw that technology come out, I'm like, I think it's time for me to move on to a different career. Because if this turns into a shooting war, we're dead really quick. Really, really quick. So, to get rid of this residual magnetism, if any of you are into boating or fishing and you ever have the opportunity to get on Hood Canal, don't get too close to the submarine base because they have gunboats and stuff and it's all restricted area. But over at the submarine base in Bangor, they've got a giant pier. It's a degaussing pier. And what they'll do is pull an entire Trident submarine into it and pull off that magnetic field and get it back to just an unmagnetized piece of steel. But over time, that magnetic field will build up again and it needs to be stripped off periodically or you're going to have a real profound magnetic signature.
How long is that? It's self-built. It has to go to a dock and have it removed.
Correct, yeah.
How long does it take for it to build up?
If I told you, I'd have to kill you. A lot of it depends where you operate to and what the magnetic, if you're doing a lot of stuff up north and there's some stronger magnetic variants, you're going to pick that up a lot quicker.
Is that stuff really classified on how long it accumulates?
Oh, yeah. Yeah, because then if you keep track of what boats go in, and it begins to paint an image.
Somewhere you get magnetized, and you're not rubbing against metal or another magnet.
Earth's magnetic field. Yeah, Earth's giant magnetic field.
So theoretically, at the equator, the flux lines are at their weakest point, being that they're at their widest dispersion from the two ends.
Yep. Yep. And then again, we see this manifest itself like with the Aurora Borealis. If any of you have ever seen the Aurora Borealis, I had the opportunity in February. I went up to Fairbanks. And they say that if you're up there between October and April for 3 nights, basically you stand a 90% chance of seeing the Aurora Borealis. So we were up there for the flight up there, we saw them from the airplane. The first 2 nights, it was phenomenal. We couldn't have planned it any better because there was a huge solar flare. And that's exactly that Earth's magnetic field is attracting the charged particles. So as soon as they get the upper regions of the atmosphere, they ionize. So literally it's like a neon light, except it's in the sky. So I should bring in some pictures and show you. It was breathtaking, just phenomenal. You're just standing there, minus 23 degrees. It warmed up. The week prior it was like minus 47 or whatever. And I seriously, even though I had gloves on and everything, I had to take off my gloves to manipulate the camera. I ended up burning the tips of my fingers. And it took about a week for me to get the feeling back. And it's very, very dangerous, but way cool. Way cool to see this. And, people spend thousands and thousands of dollars to go up there and see that. But it's the magnetic field that's actually attracting that near the poles. Retentivity is the ability of a material to retain its magnetic field after the magnetizing force is removed. So unfortunately, a submarine hull has a high level of retentivity. And that magnetic signature, you want to strip that off because it's not desirable to have a submarine magnetized. Now, magnetic shields are made of low reluctance materials. They're used to protect electronic equipment from magnetic flux lines. Okay? Sometimes we need to protect equipment from these lines of flux. because they could cause interference or even worse. Let me kind of back up for a second and see if you could connect the dots on this. We all understand that when we apply current to a conductor, we create a magnetic field, right? So, bear with me. If we have a magnetic field that happens to pass through a conductor, what do you think we're going to do? I'm going to create current. Yeah, so basically if current creates a magnetic field, an electromagnetic field can create current. This is one of the things that they kind of figured out the hard way when we started lighting off nuclear weapons. One of the side effects of a nuclear weapon was an EMP, an electromagnetic pulse. And this electromagnetic pulse was a giant magnetic pulse that would go through the atmosphere, and when it came in contact with a conductor, it induced a current where current didn't belong. Fry radios, back in the day when they first started lighting off nukes, basically we all used tubes, and tubes are high voltage devices, and it would cause some interference and some wacky symptoms, and that was about it. With us going to microchips now in integrated circuits, that amount of current is going to fry, that's our technical term for the night, fry these circuits. Okay, because we're dealing with minute amounts of current to get the job done. So all of a sudden you have an EMP, you're going to fry stuff. And quite frankly, it really concerns me. I know enough about this where, basically if you had, everybody's afraid of a dirty bomb and everything, and yeah, that's really bad news. But I tell you what, one strategically placed high altitude nuke going off over the central U.S. is going to totally wipe us out and send us back into the Stone Age. Okay? And it's the high altitude ones that really screw things up because they're far reaching because of the line of sight. And I mean, can you imagine a world, in a world that your ATM doesn't work, in a world that your grocery store, which uses a computer to order new food and supplies from the distribution center, doesn't work, your cell phones don't work, your internet doesn't work, your computers don't work, your car computers don't work. The only people that are going to be driving around are the old people kicking old school diesel, where, compression and fuel, and you've got the diesel engine running. Okay? Science fiction? No, pure science. This is how it works. So these magnetic shields are actually used in some military applications for hardening the sites, because we know that this EMP is going to cause problems. None of the consumer stuff that we use is hardened. Air Force One, what the president flies around in, is hardened. Okay, they brought that down to Kirtland Air Force Base outside Albuquerque, New Mexico, and that's where they do this EMP testing and basically prove what it's able to withstand. And again, that's all really highly classified information. The same thing with the autopilots, now it's all fly-by-wire technology. So this electromagnetic interference could cause big problems. I don't know if any of you remember years ago there was a problem with Airbus. Well, there's always been a problem with Airbus. It's just different problems as time progresses. But this was the problem with Airbus was with the A320 aircraft. And the A320 was the first commercial aircraft to use what was called fly-by-wire technology. And it's actually funny, I like messing with people that are flying on it. A lot of people don't realize that up in the cockpit, there's no control yoke like this on an A320. They're flying with a joystick. And the pilot's seat, and he's got the instrument panel in front, and right off to his left here is a joystick. And that's how the pilot, captain, has got his on the left, the co-pilot's got his on the right. So there was an air show that they were doing a flyby. And what happened is the airplane died to the symbolic low pass, and then kept going and going and going right into the trees at the end of the runway, and there was a huge fireball and explosion, and a bunch of people got killed. But there were a bunch of people, including the pilot, that survived. And he was like, man, I don't know what happened. I was pulling up the whole time. The aircraft was not responding. So in basically the investigation, they determined at this big air show in Europe, there were military aircraft that were present. And they had their high energy weapons fire control radars turned on. And they think that high energy got into the computers and basically put current where current, and it got confused. So he's pulling up on the stick, to pull up and, dip the wing and, you know the maneuver. At least I know the maneuver. It's a classic maneuver. Instead, he's pulling up and just right into the freaking trees. You can look that up on YouTube, A320 crash, and, they very well documented crash. They added a lot more magnetic shielding to it. Boeing's first airplane to dabble with fly-by-wire was the 777, and it was kind of a gamble. Military aircraft have used it for years, but military aircraft are kind of a different animal. If you got a problem in a military aircraft, eject, 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 pow, you punch out, and you live to fight another day. In a commercial airliner, you got hundreds of people behind you. There's no eject, eject, eject. It's like you got to ride it out and you fix the problem. So Boeing's first airplane with fly-by-wire technology was the 777. And believe it or not, it was kind of funny because Boeing opted for standard controls, not the joystick. They could have done a joystick, because basically the standard controls are controlling the equivalent of a joystick, but it makes the pilot feel like they're kicking it old school, and they're not kicking it old school. They're still putting in inputs that create small currents to feed a computer, and then the computer controls the control surfaces of the aircraft. So in a lot of cases like that, suffice to say, you reckon Boeing's got some really good magnetic shielding on their flight control systems, fly-by-wire? Absolutely. It's to prevent current from being where current doesn't belong. And any time there is a magnetic field, you run the risk of putting current where current doesn't belong.
So would like a lightning strike?
Absolutely.
Okay.
Absolutely. And that was actually one of the other problems, too, that Boeing had. Every commercial airliner statistically gets struck by lightning once a year. So next time you go on your dream vacation or whatever you got on that airplane, suffice to say that airplane was probably struck by lightning in the past year. As Boeing went to, and for most aircraft it's not that big of a deal, because what happens is when an aircraft is struck by lightning, it follows what's called skin effect, and that current passes over the skin of the aircraft. I mean, it could scare the dickens out of you if you're on board. It's going to be a big, and in some cases, fireball coming through the cabin, and, it's going to scare the dickens out of you, but it's not going to bring the airplane down. One of the manufacturing trends now with aircraft, though, is not to build airplanes out of aluminum, it's to build it out of composites, okay? If you're using carbon, they're not always using carbon, they're just using various composites. So one of the things that they're doing on aircraft now, especially control surfaces, flaps, ailerons that control the roll of the aircraft and such, these would typically be made out of composites. So you get struck by lightning, it's quite simple. The lightning gets in there, has nowhere to go, it blows the control surface apart. Not good if you're in the airplane. Okay, because now you're going to lose control because you don't have the ability to control the aircraft anymore. So what Boeing actually started doing is that by basically putting in a conductive layer into the composites, so that will allow current from a lightning strike a place to dissipate. So kind of get rid of the aluminum only to put a conductor back into the composite. It's still highly efficient and lighter and stronger and everything else. I guess lighter and stronger. I don't know. When they fail big. But I guess aluminum, when aluminum fails, it fails big too. So I don't know. I like kicking it old school. Electromagnetic induction is the principle behind the generation of electricity, and I think all of you know where I'm going with this because we just talked about EMP. A magnetic field passing through a conductor is going to induce current. Current is produced when a conductor passes or is passed by a magnetic field. As the conductor passes through the magnetic field, a deficiency of electrons is going to be created. This results in a difference of potential between the ends of the conductor. So again, if you've got a long piece of wire, you pass a magnetic field through it, you're going to induce current. Many years ago, I think the space shuttle conducted an experiment like that. And literally what they did is they trailed a long wire loop, and what their goal was to try to drag it through the Earth's magnetic field and see if they could, generate current from that. Basically, they vaporized the wire. That's how much current they generated from the Earth's magnetic field. So if there was a way of harnessing the Earth's magnetic field as a generator, our energy woes would be over. But I don't think there's a, adequate way of harnessing it at this point. Basically trailed a wire and pulled it through the Earth's magnetic field and vaporized the wire. So when the conductor is removed from the magnetic field, the free electrons return to their parent atom. So what we're doing is we're getting electrons to move in a conductor. By getting electrons to move in a conductor, we call that current. Call that current. So we're creating current. Faraday's law. The induced voltage in a conductor is directly proportional to the rate at which the conductor cuts the magnetic lines of force. Okay? Going to make this real simple for you to understand Faraday's law here. Okay? Envision up here that I have a big north pole, big magnet sitting here, boom, big, giant. And here I have a big south pole. You all agree that I've got lines of flux that are going from the north pole to the south pole? And all that stuff that I talked about earlier, the straightest line, the shortest distance, right? So in between here, I'm going to have a strong magnetic field if I had a giant magnet right here. Do you agree with that? Okay. Faraday's law says that if my conductor, if I got a conductor, this is a conductor. When I say conductor, I'm not talking just a piece of wire. I'm talking about a piece of wire that has a loop in it. So the current's got to have somewhere to go, and it has to have a load, right? If I get this and I move it perpendicular to the lines of flux, I'm going to generate my maximum amount of current because I'm doing what? I'm cutting the lines of flux. If I get the conductor and I move it parallel to the lines of flux, nothing's going to happen. I mean, nothing is going to happen because the lines of flux are going north pole to south pole. So me with the conductor moving it like this all day long, nothing's going to happen. All of a sudden I move it like this, I'm moving it right through those lines of flux, perpendicular. So I'm going to get maximum effect of cutting those lines of flux. So that's, in essence, Faraday's law.
Now, what would happen if you move that more towards the north or the south end of that?
It's me cutting those lines of flux. So I'm still going to have a strong effect by simply cutting it. Now, if I'm doing it at a 45-degree angle, what am I going to be doing? I'm really half effective. It's not this, and it's not this. It's going to be half at 45 degrees. Faraday's law. But I'm cutting it at a 45-degree angle, so I'm not cutting the maximum lines of flux. By cutting it at 90, I'm getting the maximum out of it. So that's Faraday's law. This here, don't try this in your car on the way home. Somebody will think you're like doing gang signs or something, you know. Yo, I'm an electronics student. Yo. This is called the left-hand rule. And the way that this thing works is that your finger points in the direction of flux. Which way does flux go? Which way does flux go? From where to where? Positive to negative? East to west? Bzz, bzz, north to south. I said that earlier, right? Flux goes north to south, north pole to south pole. So this means north to south. That's the direction that the flux is pointing in. Make sense? My thumb is going to point in the direction of motion. So as an example, let's go back to me with this, wielding the yardstick here. Is this a yard? This is a yardstick, 36 inches. That's one of the reasons that I'm real happy that we're not on the metric system, or we weren't when I grew up. Because having attended a Catholic church for school for a period of time, the nuns, if the nuns had been equipped with meter sticks as opposed to yardsticks, there's a good chance I wouldn't be here with you today. Okay, because that additional 3 inches would have been just enough probably for them to connect. And yes, I was beaten by the nuns. Anyway, so I've got a north pole here, a south pole here. Remember that, north here, south here. Okay, so that means the lines of flux are going which way? North to south. So I got to do what? Make sense? I'm going in this direction. Okay, so with the left-hand rule, now my thumb is going to point in the direction of motion. So this means the conductor is moving down through this scenario. And if that's the case, If that's the case, my middle finger is pointing towards me. Which way does current flow? This is not a trick question, folks. Negative to positive. So that means I am positive with respect to my finger, negative to positive, current going to flow towards me. Okay? To make it easier, let's make this the North Pole, let's make this the South Pole, and let's move our conductor down. By moving the conductor down, current now is going to be flowing away from me, negative to positive. Make sense? So again, will you ever use this in industry? I doubt it. But this is a way of determining which direction we're going to induce current in a generator based on relative motion. Now, magnetic and electromagnetic applications. Probably the biggest and most important is the AC generator. AC generator converts mechanical energy to electrical energy by utilizing the principle of electromagnetic induction. And this is the most popular way of producing electricity. Now, whether we turn this AC generator, we're going to turn it by the shaft, right? Whether we turn that shaft from steam and a turbine that's generated from coal, oil, nuclear, hydroelectric, it's irrelevant. The key is that we're turning the shaft. And turning the shaft, we turn the generator. That's what produces the electricity. Now, if we take that another step, are there means that are more efficient than others? Are there means that are more ecologically minded than others? Are there, what we watched last week in our program meeting on Wednesday? I mean, even that dude, who was, pretty much a tree-hugging kind of guy saying, hey, I've rethought nuclear, and although nuclear is dangerous and it's something we need to be aware of, polluting the environment with coal is worse. So things for us to think about. But the key here is by turning that shaft, we generate AC electricity with an AC generator. This is how it works. This is how an AC generator works. And the thing that I want to point out to you here is that these are the magnets. And these magnets could be permanent or they could be electromagnets. They could be permanent or they could be electromagnets. As a matter of fact, this is exactly what is taking place in your alternator in your car. Okay? In your alternator in your car, are those permanent magnets or are they electromagnets? Does anybody know? Alternator in your car, which produces voltage for us. It's a generator. Are they permanent magnets or are they electromagnets?
Are they electromagnets?
That's my question to you. What's that?
I'd say they're natural magnets.
No.
No?
No, because there's you have power going to it.
And what do you call that? If some of you have ever played around with an alternator, you might remember. As soon as I say it, you're going to know if you've played around with it before. It's called your field windings. Your field windings. Your field windings produce an electromagnetic field. This is why if you know how you can push start a car? You can push start a car if it's dead. You can push start a car if it's dead. If your battery is totally dead, you're not going to push start a car. Some of the older VWs are different magnetos, different system. Okay, different on my aircraft. My aircraft doesn't have a system like that. It has a magneto. So if I get that prop rotating, I'm creating a spark that will support the combustion process. Okay.
Like a kickstart motorcycle?
Kickstart motorcycle. So, your car, if your battery is totally dead, if you remove your battery and try to push start your car, pop start it, it ain't gonna work. Okay? If your battery is kinda dead, not enough to crank the starter, but enough to go click, 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 that's probably enough to create enough of a magnetic field so when you push the car, pop the clutch, start the combustion process, get the engine turning, immediately you're going to start to increase the voltage to these windings. So these windings could be I don't really know of any applications that use permanent magnets here. Most all use windings. The same thing for a power generating plant, like at Grand Coulee Dam. They got to start off with a little bit of voltage to create the magnetic field and then get the generation process going. They're not permanent magnets. Okay, so this loop of wire, this is an artist's depiction, this loop of wire has a light side and a dark side. This is just so you could see it for the purposes of illustration. But this here is actually a loop of wire. The loop, the armature here, is connected to these slip rings. These slip rings allow the armature to stay connected 360 degrees of the rotation. So if we look at this right now, North Pole, South Pole, North Pole, South Pole, the armature right here, with the winding here at the top and the winding at the bottom. Is the winding right now parallel to the lines of flux or perpendicular to the lines of flux? Parallel. It's right at the top. You see how it's right at the apex here, the top? So right at this moment in time, it's parallel to the lines of flux. How much current do we generate when we're parallel to the lines of flux? Faraday's law. How much? 0. And look what we're generating right here. 0. When we rotate that armature now, we're going to rotate it. We're going to connect the shaft to this, and we're going to blow on it and make the shaft turn through a wind turbine, or we're going to steam and rotate the shaft through a steam turbine or whatever. But when we rotate the shaft now, how many degrees have I rotated it from my peak? 90. So right now, is the armature parallel or perpendicular? Perpendicular. What does Faraday's law say? When I'm perpendicular to the lines of flux, I generate my maximum amount of current. Well, look what we did. When we rotated it 90 degrees, now I'm at my maximum peak value. When I rotate my armature another 90 degrees, see how I started out here at the top? Then I rotated it 90. Now I rotate it another 90, so I'm actually 180 degrees from where I started off. Am I parallel or perpendicular to the lines of flux? Parallel. What does Faraday's law say? 0. What am I generating? 0. I rotate it another 90 degrees. Now I'm coming up on the back side, 270. Parallel or perpendicular? Perpendicular. What am I going to do? Generating Faraday's law, maximum, cutting my maximum field. I'm right here. I complete that cycle. I've just created 360 degrees of a sinusoidal waveform. This is an AC generator. Half of this is positive, half of this is negative. If you're actually an electron caught in this whole thing, basically what happens is you get moved X amount in this direction, then you go back to 0, and then you get moved X amount in this direction, and then you go back to 0. You never really go anywhere, but you do get shaken back and forth, back and forth, back and forth. Make sense? It's an AC generator. A DC generator, and actually, by the way, does anybody know who the father of the AC generator was? Who do we give credit to AC generation?
Tesla.
Tesla, very good. Nikola Tesla. He said AC was the way to go. There was another guy, big in history, who said DC is the way to go. Anybody know who that dude was?
Edison?
Edison. Actually more of a household name. Everybody knows Thomas Edison. Actually, when I first entered this industry, nobody even knew Tesla. Tesla recently has gained some acclaim or a cult following, depending on how you want to look at it. But Thomas Edison, he wanted to wire up everything in DC. If you go back to New York City, which is actually the power company back there is Consolidated Edison, Con Edison, really started out by Edison. Edison got the first contract to wire up the New York City, and he wired up a lot of the buildings for DC. And again, we're not going to get into it here in class. You could look at YouTube, Edison experiments, electrocuting animals, Tesla experiments, and they were. They'd get like an elephant and like, you know, electrocute it and like, you know, kill it dead and say, see, this is why you don't want to use DC. This is why you want to use AC. AC is much safer, you know, and sort of like killing animals and stuff on, you know. So you can look that up on your own YouTube. We're not going to do it here. But I mean, it was. These dudes were at each other because it meant world domination. You know, who's going to get the contracts. And again, Tesla was right. AC is much more efficient to transmit. We'll talk about that later on. So DC never really caught on. But a DC generator, this is how what a DC generator looks like. Again, you've got an armature, but note here, as we rotate this, we're coming in contact here with, this is called a commutator. And the commutator only makes contact for 180 degrees. So what happens is, as we rotate the armature through, we're going to generate a positive pulse. Then what's going to happen is we're going to break that electrical connection because the commutator only makes contact for 180 degrees. And then what we're going to do is harness another positive pulse. So it's positive pulse, positive pulse, positive pulse. It's a definition of DC. Definition of DC. AC is half positive, half negative alternation. This is positive, positive, positive. This is almost like a battery. Not quite. This is a pulsating DC, as where a battery would be constant DC, created chemically. So the big thing you need to remember is that an AC generator has slip rings, and it maintains contact for 360 degrees of the rotation of the armature. A DC generator has a commutator, and it maintains contact for 180 degrees. But the same principle is applied. We're either cutting the lines of flux or we're not. Now, a relay. A relay. Anybody here have any experience working on any relays? Okay. Relays are popular. And they still are popular because for handling high amounts of current, it's still a very viable way of control. A relay is an electromagnetic switch that opens and closes with an electromagnetic coil. So real simple. With a relay, I create an electromagnetic field with a coil. What I have is an armature above that coil, and that armature has a contact on it. And it has a spring that basically, when the electromagnetic field is energized, it pulls the armature down, making an electrical contact. When I de-energize it, it has a spring that opens it back up. Energize, makes electrical contact, de-energize, opens up the circuit. Or I could do it the opposite way. I could be making electrical contact, and when I energize the electrical circuit, it's going to open the circuit. Relays also could have multiple ganged contacts, so when I energize it, I'm opening and closing a bunch of contacts. But a relay is an electromechanical switch. It's using electromagnetism to move that armature up and down. The good news is it's an electromechanical switch. It's going to fail often, and you're going to need highly qualified, competent technicians to go in and troubleshoot it. It's called job security. They replace that with something that's solid state, it's not going to need to be replaced. So as long as there are relays, there's stuff for us to fix. We use relays when it's desirable to have one circuit control another circuit. Typically one low power circuit controlling another high power circuit. These lights would be an example, although I don't know if we've got a relay integrated in. I know that there's a relay that's integrated with a motion sensor. So when the switch is energized, that motion sensor, you'll actually hear if you walk in here and the lights are off, especially over here, you'll hear the click when that obnoxious. Somebody's looking for a project, rewire this thing to keep that thing from ever shutting off when you're in the lab. It becomes pretty obnoxious. It's also used to control several circuits some distance away. So an example of like a relay would be, anybody here play with model trains at all? Model trains are nothing more than a small example of the real thing. If you look at a freight yard on how they switch and build trains, they basically have switches that move an entire, it's a motor that will move an entire railroad track so that trains, could be built on different sidings and such. Well, how do you control that? The switch alone would be like a Frankenstein, switch. You can't do that. Typically, in a switching yard, you'll have up in a control tower, a small switch that they throw that sends a small signal out to a big relay that ka-chunk makes connection and allows all that current to flow and turn the motor, which boom switches the track. It wouldn't be practical to have wire this thick going to a control tower, knocking, it would pull the control tower down. Wouldn't make sense. So it's used to electrically isolate the two circuits. Make sense? Okay. Example of this would be a doorbell. Small signal voltage bringing about a large change. The large change is you getting woke up out of a sound sleep because the delivery man's outside delivering a package. Here are some examples of relays. Some of these relays are actually encapsulated so they could be put in a explosive environment, because when you open and close that contact, what are you doing? There could be a spark. There could be a spark. So if you're working at an oil refinery, you probably don't want that spark. You want that spark to be contained, so it's going to be in a sealed relay. This one right here, you can probably see the contacts. There's two contacts here, and that thing is going to open, close, big sparks. Now a solenoid is a coil when energized pulls a plunger that does some mechanical work. An example of this might be door chimes. I'm talking about the old school ding dong, right? Those are physically little hammers hitting chimes. Now most of the stuff, even like clocks, if you buy a clock that has chimes, it's not chimes, it's a recording of chimes, synthesized, okay? There's very few examples of real chimes being struck by solenoids. Another example is your automotive starter. When you turn the key, typically you turn the key, that energizes a starter relay. The starter relay energizes the starter solenoid. The starter solenoid on your car is probably about the thickness of this laser pointer, and on the top is going to be a big piece of metal that when you energize it, it's going to pull that metal down and make a big electrical connection. That big electrical connection basically takes all of the energy from your battery and dumps it into your starter. There has to be physically a lot of metal present to make that electrical connection. So a relay has a moving armature. A solenoid has a moving plunger, a moving core, if you will. If any of you have ever played a pinball machine, the flippers, solenoids. When you hit the button, the flipper, it's energizing a solenoid. That solenoid is attached physically to the flipper. That's going to move back and forth, energize, de-energize, energize, de-energize, energize, energize, de-energize. Pinball. Anybody here like pinball? It's the bomb. It's pure. It's the pure game. Look for a project. There you go. Restore a pinball machine. You could restore a pinball machine, contemporary pinball machine. It's got everything. Electrical, mechanical. You've restored one?
I have 3 that need to be done.
Really? There you go. There's projects.
Big project.
There's projects right there. What era?
60s and 70s.
Really?
Old school.
Huh? I've got one. I've got F-14 Tomcat. It's the real deal, man. If any of you remember that one, it had the big gumballs on the top, red, white, and blue. When you get it into the advanced levels, those things light up. It was actually considered the most obnoxious pinball machine ever created. Because if you're in a bar, those freaking lights, it looks like a police car parked there, whatever. When you get into the, you know, multi-ball. It's pretty slick. What's that?
Valley or Williams?
Williams. Yeah. Good stuff. 87.
That's after Williams bought Valley.
One of my other favorites, I've been keeping my eyes open. If I find one and bring it home, my wife will kill me. Because that one pinball machine, she's freaking, when are you going to get rid of that thing? Never. I mean, it's so freaking cool, man. And I keep it operational, you know. But the other one I'm always looking for is Cyclone. If any of you remember Cyclone?
Oh, wow.
And it was a big, you know, during the Cold War, Ronald Reagan. And actually, there's a Cyclone roller coaster. And then the front car is Ronald and Nancy Reagan holding on for dear life. Great pin, great pin. Anyway, pinball brought to you by the amazing solenoid and relays. I love the applications for these things. Actually, one of the things too with relays that's kind of fun is some airports have what's called pilot control lighting. And one of the local airports here is Bremerton National. I don't, you know, probably a lot of you don't even know Bremerton National. You can land a 737 over there, okay? It's a big airport, you know. They don't have any commercial traffic in and out. They've actually tried in the past, but it's just Bremerton's not that big of a market. But it's a big runway. Pilot control lighting. So one of the things that I've been known to do in the past, if I'm bringing somebody that's not accustomed to aviation, is what I'll do is I'll start the approach, and I'm flying the instrument approach. So I'm following an invisible glide path down to the runway. So when the lights are turned off at the airport, it's just a black hole. You're just descending into this black void. And then usually about a half a mile out, what I'll do is I'll dial in the frequency, and then I'll hit the code. And basically it's a matter of me just turning my transmitter on and off, on and off, on and off 5 times, turns it to high intensity. So all of a sudden you're descending into this black hole, and then before you, this runway appears with the chaser lights and everything, and it's kind of a power trip, you know. I think it's kind of cool, you know, by me simply, you know, clicking my radio, I just turned on, you know, this huge airport, you know, 5,000 feet of runway lights. That's all brought to you by, well, there's the pilot control lighting aspect of the radio, but what really makes it happen is relays. It was really, you know, really relays. It was actually fun with relays too. Also called, could be called an industrial contactor. I used to be really in the, I guess I've gotten old and I'm out of the swing of things with holiday lighting. I used to cover every right angle of my house. I mean, it looked like, you know, Christmas vacation material. It was kind of funny because my next door neighbor, he worked for Boeing, as electrical engineer for Boeing. The guy across the street was an electrical engineer for the Federal Aviation Administration. So these guys, you know, I'm out there kind of messing with them and stuff, and you know, you see them plugging in an extension cord and a bush lights up, and you know, you plug in another extension cord, another, you know, the roof line lights up, and with me, I wanted to control everything simultaneously. So I got this big industrial contactor that fell off the back of a truck. And what I have are 4 separate circuits. Each circuit is up to 20 amps each. So what I did is I basically rewired my home, and I have separate circuits for the outside lights. And then I have it on a timer. I mean, I could connect it to the freaking, you know, clapper if I wanted to, right? So simply when that turns on, boom, everything is on at once. It's like, how did you do that? This here's an industrial contactor, you know. It's kind of a cool system.
Have you seen that video of the guy's got his computer control?
Yeah, yep, absolutely.
With music?
Yep. And actually one of the things that brings that about, and it was kind of where I was segueing into, is normally for a first quarter student, you'd be taking the PLC class, ELEC 116. PLC basically is an industrial computer that controls, open and closes, basically relays for industrial control. So after taking that ELEC 116 class, if you wanted, you could buy a PLC and basically set up a Christmas display on par with you know, what we've seen on video is that with the light synchronized to music and everything. Really easy to do with PLCs. Real easy to do. Well, not easy, but doable with PLCs. Phonograph pickups. I'm sure some of the younger students are sitting in here and saying, what is a phonograph, right? You know, what's this with the scratching, right? That's what they're scratching on a phonograph, right? Uses an electromagnetic principle, believe it or not. A magnetic field is produced by a permanent magnet attached to a stylus. The stylus tracks through the groove of a record in response to the audio signal recorded. Basically, back in the day, some of you are probably familiar with this, like a musical group were cutting an album. And literally what they were doing was cutting a groove into a blank, and they're cutting an album. They're recording an album. Okay, this is how it was done back in the day. Then what that would be is a negative. Then with the positive, you could start stamping out albums all day long and, you know, getting them to radio stations, play your music and start selling it, and that's how you'd make the big time. Well, with the MP3, that's all changed. We won't comment on that. But the stylus literally tracks through that groove in the record in response to the audio signal. The movement creates a small voltage that varies at the audio signal response to replicate the wave pattern that originally created it. The induced voltage is then amplified and used to drive a loudspeaker, producing the audio, a facsimile of the audio signal that produced it. And, you know, if anybody here own any albums? Do you have the ability, okay, anybody here have a means of playing any of those albums? I actually bought a phonograph a couple years ago because I had some older records, and you know, all the stuff's available as MP3 now, but you know, they don't. You know, and yet for that full experience, you need a phonograph player to play it. So, kind of a classic, old school, retro way of going, but
Digital doesn't produce warmth.
no, it's almost too clear.
Analog produces warmth.
Tell you, some of the stuff, I have a hard time, because again, growing up in Connecticut, you know, I had my little 8 transistor radio. We'd go down to the beach in the Connecticut Shore, Rhode Island, Musquamacut Beach. We'd go down there and whatever. And you're listening to the New York radio station. You're listening to the hits, the top 40 hits, you know. And you know, now I listen to some of the high quality recordings. It's kind of like, is this a remake? Or it doesn't sound like the original. You know, the original, because the original I was listening to out of a little speaker like this. You know, 8 transistors, mono. You know, now the stereo version of it, it's a little bit different. And of course, I was on a limited budget, so I wasn't always going out and buying the albums or certain albums that you had, and that was high fidelity back in the day. So how a record player would work, magnetic, that little stylus tracking in there, magnetic cartridge. Loudspeaker, basically the opposite, constructed of a moving coil around a permanent magnet. So basically, if any of you have ever bought speakers before, one of the attributes you look in, basically he or she who has the heaviest magnet, the biggest magnet, wins. Because that's the permanent magnet. And what that means is that you could throw more energy in there to create either an attraction or a repulsion and move the cone of the speaker back and forth, rapidly replicating the original sound that created it. So that's how a loudspeaker works. So the key components, the size of the magnet, the coil, how much energy measured in watts, acoustic energy. But again, it's a magnetic device. That's how it works. Magnetic recording uses the electromagnetic principle to store information. A signal is stored on tape or disc with a record head to be read back later with a playback head. Some can be combined in one package. That means record head and playback head on the same head. The way that this works, and it's kind of important that you understand this. Basically, it's like getting a piece of tape and sprinkling a bunch of iron filings on that piece of tape. By passing that tape over a record head, when I speak into a microphone, I'm creating a signal in the wire. Because the microphone, which also is a magnetic device, the vibration the air molecules moving back and forth create that vibration. The microphone picks it up and transforms that into a small electrical signal that goes in, gets amplified, and gets connected to the record head. The record head is going to fluctuate its magnetic field, putting those iron filings on the tape into a unique pattern. That pattern will be stored on that tape, not indefinitely, because if it's stored here on planet Earth, what's one of the things that it could be under the influence of? The Earth's magnetic field. If you put it in close proximity to any other electromagnetic device, it could alter that. So magnetic recordings will not last forever. As a matter of fact, a magnetic recording, every time you play it back and you try to read that fluctuation in the particles that was put on there, it loses a little bit of what it was originally. Remember how the video stores, and get younger students know, what's a video store? Well, back in the day, we used to have to go to places and rent VHS tapes, okay? Why would you have to rent tapes when it's just get it on demand? Well, that didn't exist back then. You used to have to rent it on tapes, right? Be kind and rewind, absolutely, okay? And those were the good old days. They really were, I think. Those tapes, they used to sell, they'd only get so many uses out of them, and then they would sell them as previously viewed. You know, and I used to capitalize on that to my library. If there's a movie I really liked, buy it previously viewed. But you know what? The quality was always on its way out, because every time you use that, play that tape, you lose a little bit of it. So like for high-end production in video, what they would do is, let's say you're making a documentary for the Discovery Channel and you're shooting it on video. Now, there's some different ways of doing it, but if you're shooting it on videotape, what they would do is they'd go out and they'd shoot, you know, with a helicopter and these beautiful shots or whatever. They'd get the original tape, they'd make one copy for the purposes of editing. Then they'd put the originals in a vault, and they wouldn't touch the originals. Then they would figure out, well, we want to edit this scene, we want to edit that scene, we want to do this. Once they figured out where all the edits were, then they'd go back to the master tapes, and they would make a recording of the segments that they want and produce a video production, knowing that every time they run that tape through the machine, they're lessening the video quality of what was on that tape. So videotape, any magnetic recording media, will over time lose its integrity. There's no way around it.
Or CDs and DVDs, kind of the same deal.
Yep, if you're burning them, with basically traditionally, it's not magnetic per se, but over time it will deteriorate. The best method is what's known as actual RAM, like DVD RAM. And that's for archival purposes. You want to, do DVD RAM. So that's one of the problems that I actually, as soon as they had a DVD burner that was on the market that was reasonable, like VHS to DVD, because when my kids growing up, I shot a lot of home movies and stuff. And over time, I knew those tapes were going to diminish. Every time I watched them, those tapes are going to diminish. So I got them and then transferred them. But to be honest with you, I should have transferred them to DVD RAM, RAM. And it's kind of a niche thing, but that's going to last the best, and it won't experience degradation. All these other forms of media, even if you're burning your own DVDs, they will degrade over time. So the way that magnetic tape works, that tiny gap between the ends of the core is a magnetic field. A piece of material covered with iron oxide, basically iron filings, is pulled across the record head, magnetizing it. Information is written in a magnetized pattern. To play back or read the information, the material is moved past the gap in a playback head. The magnetic field induces a small voltage into the coil winding. When amplified, the information is reproduced. And this really revolutionized the recording industry, being able to, I remember back in the day, I'm dating myself, but wow. Could actually own a cassette recorder, and I could speak into a microphone and record my voice on magnetic tape, and then you could put it in and at a later date and hear yourself. Wow, that was really the big deal. Now, we have cell phones that we talk into and digitally record that. Examples that used this technology on tape would be cassette recorders, video recorders, reel-to-reel recorders that were used in a lot of production studios and such. Floppy disk drives. Floppy disk drive is nothing more than a disk with particle on it, with iron particles on it. And believe it or not, hard disk drives. If you've got a hard drive in your computer, it's using the same technology. A little bit better? No, a lot bit better. Okay, because now you could go out and buy a terabyte drive for $49, and the reliability of that data is extremely high. And if it's properly maintained, you're really not going to lose integrity of that data. And it's really, as far as I'm concerned, that's the best method of storage. My wife and I really enjoy amateur digital photography. And when we go out and shoot something, when it's on the card, we're at risk. As soon as we plug that card in and we copy it to one drive, my primary drive, okay, then what I do is I mirror that on a secondary drive, and I mirror that on a tertiary drive. And I also pay for a service to go back to that primary drive and back it up off-site. Okay? Let me tell you, in the middle of February, right, I fly to Fairbanks, Alaska, minus 23 degrees to see the Aurora Borealis to get some pictures. I don't want to lose those pictures because my hard drive fails. So I want to make sure I have backups to backups to backups. So as long as you do that, you're good. With me just transferring a home movie to a DVD, I could lose integrity of that over time. If it's backed up digitally on a hard drive and you could, again, mirror that, then you're good. DC motor operation depends on a principle that a current carrying conductor placed in and at right angles to a magnetic field tends to move at right angles in the direction of the field. Basically what we're saying is if we could rotate a shaft and create DC, why can't we apply a voltage to a winding and create motion? So the difference between a DC motor and a DC generator is perception. Most cases they could be used either way. It's actually one of the things that they use for power management over at the Grand Coulee Dam. I don't know if any of you go recreating over in central Washington. You ever go camping or anything out there? It's really amazing. If you have a chance to go out there, this is stuff, again, they were thinking about in the early 1900s. Okay? You got the Columbia River. They built a dam on it. Not just any dam, the Grand Coulee Dam. Okay? And what they did behind the dam is they created Lake Roosevelt. For the purposes of irrigation and to store energy during low demand times, what they did is they have the generators turn. You can't stop the Columbia River. It's a river. You're going to kill all the fish. So you can't just shut the river off. You got to keep the water flowing. But if it's low demand time, get that, harness the electricity, then with the electricity, drive pumps. And they pump the water from Lake Roosevelt up to Banks Lake. Banks Lake, very popular for water skiing and recreating. Banks Lake goes to feed agriculture, and then during peak demand times, what they could do is turn it backwards and catch the energy flowing back to Lake Roosevelt, producing energy, and then catch it falling back into the Columbia River and harnessing it twice. So basically you're using the water to store the energy by simply pumping it to a higher elevation during that low demand time. Brilliant. Brilliant. You know? And again, they figured this stuff all out in the early 1900s. So that's what they've got between Lake Roosevelt and Banks Lake, basically are motor generators that you can turn either way, and either turn it backwards, pump the water up, or catch the water falling and generate electricity.
Those giant pipes that are off to the side over there.
Yeah. And this is simply the process of creating a magnetic field that attracts and opposes and creating motion instead of motion being used to create a magnetic field. Now we're harnessing the magnetic field to create motion with a DC motor. Another area that uses electromagnetic fields, TV, radar, computer terminals. What we're talking about is the old school monitor like that. Old school monitor like that. Basically in the back of a monitor like that, there's an electron gun. So you get to go home tonight. What'd you learn about in school? My instructor was talking about them, their electron guns. It's going to zap us. Now, an electron gun basically sits in the back of a cathode ray tube and shoots an electron beam out towards the screen. That electron beam is going to be controlled through deflection windings. The deflection windings are horizontal and vertical. And that's what's going to be used to basically paint the image on the screen. It's your x-axis and your y-axis. So that's how we'd use that to paint an image. Now with flat screen monitors, we're doing things a little bit different, but it's kind of an evolutionary process based on what we were doing with that magnetic field. In summary, we talked about magnets, natural magnets, unnatural magnets, artificial magnets, and electromagnets. Come in many shapes and sizes. Big thing to remember, unlike poles attract, like poles repel. Two theories of magnetism, electron spin and domains. Flux lines are those invisible forces that we can't see. You know, this lecture wouldn't be complete if we didn't talk about, anomalies. You've all heard of the Bermuda Triangle, right? Well, science or science fiction? I mean, they've got some really good hard evidence of magnetic anomalies that occur there. So if you're navigating solely by compass and you encounter unusual magnetic fields, or you're flying an airplane that's, again, has a gyro compass in it, it could cause problems, big problems for you, magnetic disturbances. There's actually on aeronautical charts, they put down areas that have big magnetic disturbance areas that they're used to. The Bermuda Triangle is one of them. It's actually one of the things that's kind of interesting too that I see a lot of these like ghost hunters using is equipment to basically sense magnetic fields. And there's a school out there that basically says that spirits possess this energy, and this energy manifests itself as a magnetic field. So if you have sensitive enough equipment. And, I don't know, anybody watch any of those shows on TV? I've watched enough that something's going on. Something's going on. And actually, quite frankly, I think we're very naive if we only believe what we could see with our five senses. So, I think there's probably some truth in some of this stuff. We talked about the magnetic field, determining direction of flux lines. We talked about electromagnets, strength, polarity, retentivity, electromagnetic induction. We talked about Faraday's law, right? Parallel, perpendicular. We not only talked about the left-hand rule for generators, but I gave you a specific warning of not doing that in your car on your drive home. As someone might think you're giving gang signs. We talked about AC and DC generators. Big thing to remember about an AC generator, right? Slip rings. DC generator, commutator. AC generator makes a wave that's half positive, half negative. DC generator makes pulsating positive waves. Relays, basically electromechanical switches. A moving armature, or a series of ganged armatures, contacts on armature. We talked about how we could use this for doorbells, solenoids, phonograph pickups, loudspeakers, magnetic recordings. And then finally we talked about DC motors and yes, meters. That DR's involved meter movement is nothing more than a permanent magnets and a coil. When you pass current through that coil, you either attract or oppose, causing the needle to move. And then finally we talked about the electron beams created by electron guns, which are in the back of a CRT. It's how we used to create television signals, radar displays, oscilloscopes, and computer terminals. Anybody have any questions on anything that we covered in this chapter? There's a lot of new terms to familiarize yourself with this. Less math, more remembering new terms. Question?
This doesn't have to do with this topic, but do flux lines in here have anything to do with the flux capacitor and Back to the Future?
I have the flux capacitor in Back to the Future. I have no idea what that is, and I probably wouldn't recognize it, you know, if I saw it. So yeah.
There's no reference to the flux capacitor. It's just a completely made-up thing that they came up with, huh?
Pretty much. I don't know if there's any Wikipedia references to it.
Yeah.
You know, could be a fun project to try to build one, I reckon.
I was just wondering, you know, some of the things, you know, CRTs are called cathode ray tubes, but it's really the electron beams that do it. So why would they call it the electron beam?
Well, you guys are stumping me tonight. I don't know. That's what they've always caused it. Yeah, it should be like an electron beam tube, cathode ray tube. Cathode sends out an electron ray, and it's a vacuum tube, cathode ray tube. Electron beam. Yeah, I don't know. Got me. Good question. Yeah, let me tell you, if I was the Pope of electronics, all of this stuff would have been called something easier or simpler. You know? Some of the stuff you just got to hit the I believe button. But suffice to say, like say magnetism, it is really, really critical. That's actually one of the things too that I don't know if you, I can't confirm or deny, but the movie Hunt for Red October, you know, that was basically a hydrodynamic drive that was based on magnetic field. And, you know, you could look at that and say science fiction. Science or science fiction. I, of course, cannot comment on it. But if you research that type of technology, the Japanese, of course, is an island nation. They're very dependent, and always have been dependent on trade. They've played around with that technology on barges to see if they could, you know, move a barge using this, you know, hydrodynamic drive system. And, you know, again, it's not mainstream, but they've played around enough with it. So.
I heard that, yeah, I would think that, you know, it might be possible to think it's really silent, but it basically send up a flare in the magnetic field because you're creating such a huge magnetic disturbance that it's not going to make the sub any more invisible.
And to be honest with you, you know, and I haven't rowed a nuclear submarine in over 20 years. I know that we had submarines out there that were so quiet you wouldn't hear the submarine. What you would hear is the submarine blocking biological noise behind it. So it's like if you had something big going past your ear, you know something is there because it's blocking the sound. So, I mean, that was 20 plus years ago. So we've never had a problem keeping quiet and keeping things real quiet. But performance is another issue. See, if you want to go fast underwater, you're going to make some noise, and that will give give you your tell basically. So, any questions? Any other questions, comments, concerns?